Alright, Calculus 12 again, and I thought I'd recap a quick little question in regards to related rates, section 3.5 in the textbook. So here is just a quick breakdown of the strategies, which again I know is the hardest part. So I'll just state them here, then we'll go through an example to reiterate those. First thing is, again, you want to draw a picture and label all the variables that are changing in the picture. You want to list out what you want and what you have, and don't forget related rate questions will always be with respect to time, like something per second or per hour or per minute. The next thing you want to then do is, if you have all the information that you know that you need, you can literally move on to the derivative part. But if you don't have all the information, you might either have to do some indirect thinking, or you might have to find another relationship to take away one variable, very much similar to a max-min problem in that sense. Once you get to that point, then you can take the derivative, and this is the key point, with respect to time. So it'll be some derivative of something with respect to time, something dt. Once you have that taken, then you can either solve for your unknown and then plug in the data, or plug in the data and then solve for your unknown, and then state the units on your answer. So the problem that I was going to do is this guy here, and again the words look worse than they are. It's like a dog with a bad bark. You just got to get to know this little doggy and then it's fine. So nice little doggy. So I'm going to read the question, take a deep breath, and draw a picture. So a ladder rests against a wall that is vertical. The wall is vertical. If the bottom of the ladder slides away from the wall at a rate of 1 feet per second, or 1 foot per second, how fast is the top of the ladder sliding down the wall when the ladder is 6 feet from the wall? So again, I'm going to draw a picture of, first of all, a vertical wall and the ground, and then here's my ladder that is sliding. This part here is sliding away from the wall at a rate of 1 foot per second. So if I put the pen here as the ladder is falling down. One side hits the vertical, and then it slides down, as you can imagine. Just like Chevy Chase from Christmas Vacation, falling down the ladder. Foomp. So at that point, I'm going to then think about what's changing. The distance from here to here is changing throughout that entire movie. So I'm going to call that, for lack of a better letter, I'll call it, I don't know, X. Sounds like a good one. This distance here is also changing as the movie plays out. That distance is going down, so I'm going to call that Y. The ladder length, because we're assuming the ladder, which they should have told us actually, and I missed that in the problem. I should insert in here, it's a 10-foot ladder. Without that question, it would be impossible to do without concrete data. So it's a 10-foot ladder, that should be stated. That's always 10 feet. Now, if the ladder was shrinking or growing as it was falling, that would just add a whole other variable dimension to the question, which could be done. And I know this is 90 degrees because it's a vertical wall to the floor. So I look at that. My first gut relationship, almost jumping to the third step is the relationship, is I just see Pythagoras right now. I see nothing else but Pythagoras. Now, as I think about that relationship, I'm going to list out what I have and what I want. So I'm going to come back to this in a minute. So first of all, they told me this is 1 feet per second, the changing. So dx dt right here, that's 1 foot per second. They want me to find how fast the top of the ladder is moving, so they want dy dt, and they want it at the instant the ladder is 6 feet from the wall, which is meaning when x is 6. So let's just see if I have all the data. 10-foot ladder against the wall. The bottom slides away at 1 feet per second. How fast is the top of the ladder sliding down the wall when it is 6 feet from the wall? So there's what I want. There's what I have. Before I even get into this, I could even think about, they told me the value of when the ladder is 6 feet away from the wall. I could also find the y value with Pythagoras. So I'll keep that in mind. So I do have y, I just have to work for it with x, but I'll come back to that. So now I got to ask myself, if I took the derivative of this now with respect to time, would I have everything I need? So if I took the derivative of this, which I'm going to in a minute, but I'm not going to do it yet, I would get x's and dx dt's out. And I'm okay with dx dt's because I have it. I'm really okay with x's too because I have it. I would also get y's and dy dt's out. I'm okay with dy dt because I want it. I'm even okay with y because I can find it. Alright? So I'm safe. And then I can take the derivative of 10, no troubles. It's going to be 0 of 10 squared. So I can take the derivative of this with respect to time. And this is the most important part. So as I take the derivative, I'm going to take the derivative of this side. Oops. Equals. And I'm going to take the derivative of 10 squared. This side is easy. That'll be 0. The derivative of this, remember this is with respect to time. So this is where I got to be careful with that little sneaky baby chain rule. So if this was with respect to x, this would have just been a 2x, but it's multiplied by the inside, which is dx dt. The derivative of y squared, for the same reasons, is 2y dy dt. And now I'm going to solve for dy dt. So I would subtract this to the other side. So I'd get 2y times dy dt equals negative 2x dx dt. Divide out both sides by 2 and divide by y. So I'd end up with dy dt equals negative x times dx dt, all divided by y. And now I literally just need 3 things to answer this. I need x, which I have is 6. I have dx dt, which is going to be 1. And I just need to find y. But remember, we talked about y. Y is just a little bit, I'm just going to do that on the side over here. Here's finding y. I know that x squared plus y squared equals 10 squared. I know that at the instant x is 6. I can solve for y. Y is going to be equal to whatever 100 minus 36 square rooted is. And that's going to give me square root of 64, which is 8. So I have all the information I need. So dy dt equals negative 6 times 1 divided by 8 in lowest terms, negative 3/4, and the units are feet per second. Now the reason it's negative is because the y value is shrinking. So shrinking. And the ladder, how quickly is the ladder sliding down? At 0.75 feet per second. So that is an example of a related rates question. And again, let's just recap. Drawing a picture, labeling the variables, listing out what you want and what you have, finding a relationship. And if you have the relationship and all the information that you need, you don't have to find another relationship necessarily before you can move on. Here we're kind of fortunate. Once we had that, taking the derivative with respect to time, I could plug all the data in and get there. Sometimes I have to do a little bit more work in here to get rid of one variable, and that might mean similar triangles or some other kind of geometry situation, but this one was already ready to go. Hopefully that helps, and just remember that is 3.5 from the textbook, related rates. Okay, over and out, done.